Hello.
Hey, Jafri.
Hi, how are you?
Good, good, good. You?
I'm good. Okay, so let's start with this.
All right.
And first we are going to do the chapters question. The first, I was just looking like
Yeah, this chapter 12 is dealing with intermolecular forces.
intermolecular forces and liquid and solids.
Yep.
Okay, and the question number which you told me like here is 12.11 and onwards. Am I right?
Yes. Yep. 12.11. I got a copy of those questions opened up.
Okay, and we also okay, no problem. We can see what question they are giving. 12.11.
Yep. Ammonia is both a donor and an acceptor of hydrogen in a hydrogen bond formation. And he kind of briefly went over each one. He said to
draw a diagram to show the hydrogen bonding of an ammonia molecule. Ammonia is both donor and acceptor of hydrogen in hydrogen bond formation.
He mentioned he wanted us to draw like the possible locations where the ammonia could hydrogen bond with each other.
Okay, so let's start with ammonia is like N, and because if I write the Lewis structure, is going to be 3 hydrogen bonds, single bond. And if you take a look, nitrogen has 5 valence electron, and each hydrogen has 1 valence electron. So 3. Total we have 8 electron. So 8 electron means 3, 2 to 4 to 6, and 1 we have a lone pair of electron. So nitrogen can donate this lone pair and act like a base. It can donate to the hydrogen, and also it can accept hydrogen. So that is both donor and an acceptor of ammonia is both a donor and an acceptor of hydrogen in hydrogen bond formation.
Okay.
So for example, if you are taking like a H positive ion, HCl or something, H positive ion. So it can accept like the, for example, if I am taking water, HOH, I am writing this one. So in this case, oxygen has 2 lone pair of electron. Oxygen is a partially negative and hydrogen is partially positive. Nitrogen is partially negative, and it gives its electron pair to this one and make a bond between them. So this bond is going to be between the negative and positive. Negative nitrogen and positive hydrogen is going to be, you can say, like a hydrogen bond. It's not making a bond because hydrogen cannot make 2 bonds, but it's like a negative and positive, and you can say attraction like this one. Actually I have to write like a dotted line something, not like a dotted line here with the water. So this is a negative part, and because it has a lone pair also, and this hydrogen has partial positive charge. So the hydrogen bond is between hydrogen and either nitrogen or fluorine or oxygen. Only 3 atoms which are the most electronegative atom: fluorine, nitrogen and oxygen. If it is chlorine, It's going to be like a dipole attraction, but it's not going to be called as hydrogen bonding. So hydrogen bonding is only between hydrogen and either one of them.
Only those.
Is it clear? Yes.
Okay.
And similarly, if I take like hydrogen bonding, so in this case what happening? Ammonia is both a donor and acceptor of hydrogen in hydrogen bond formation. If suppose I am taking something positive is there. So in that case what happens? Hydrogen is going to donate that one. Is going to donate that thing. So that's they are showing this thing. Draw a diagram to show the hydrogen bonding of an ammonia molecule with two other ammonia molecules. Because they are asking with the ammonia molecules, not with other molecules. So let's take that one. And because they are not asking with other molecule, just asking with another ammonia molecule. So let's write ammonia molecule. This one partially negative, and I am writing here another molecule of ammonia. This also has negative and this is positive, and they are making a hydrogen bond here like this one. So in one of them, if you take a look, they are asking how many? With two other ammonia molecules. I already made only one and 1, 2. So I'm making another one. And H, in this case. So look here, in this case positive, negative, and again they are making hydrogen bonding. So this is like one ammonia is making, in this case, the central ammonia I'm talking about.
Yep.
It is like donating hydrogen to this one, making hydrogen bond with a nitrogen. In this case, it is accepting hydrogen to make hydrogen bond.
Okay.
So at the same time, it is donor and acceptor.
Okay. Yep.
And now look what picture they are showing you.
That's exactly it. Yep.
Is it the same thing?
Yep.
It's
yeah,
clear?
and they use the.
But hydrogen bonding don't make a bond. It should be like a dotted line, something.
Yeah, that it's not a bonded line like these are right here. It's the like you said, the dash or the dots.
Dash, yes.
Yep.
Yeah, dots are that like that.
Yep.
So one molecule, because they are not talking about this one, two molecule. But in case if somebody asks, like, I can also show that one, okay? But in this question, they are asking this one. One ammonia, in one case it is donating, in other case it is accepting to make hydrogen bonds.
Got it.
Is it clear?
Yep. Yes, sir.
Okay, before we proceed to the further question, last time we did like from chapter 10, am I right?
Right. Yep.
And one of the question was about the geometry of the molecule. I was like teaching someone else and giving the question from what I have with me. So I was looking like AB2 and asking what is the geometry of this one.
So linear, right?
AB2 is going to be linear, maybe linear, but also there is other possibilities. Not why? Because when you learned from the documents which you have sent me, it says like a zero lone pair. They are zero lone pair, and then they are talking about AB2 and AB3, something like this. Am I right?
Right. Yep.
And if it is AB2 and E means one lone pair.
Yes.
But when I had given the question to my other student, I didn't notice at that time, and then I realized because they were not saying zero lone pair at that time. If you look your the documents which you already have sent me, like the figures, it clearly shows zero lone pair. But if it is not mentioning zero lone pair, so maybe there is one lone pair, maybe zero lone pair. In that case, it is going to be linear. But what about if it is AB2 and also has one lone pair? Not shown. What will the structure in that case?
Trigonal planar.
Trigonal planar, and otherwise, if you take like,
bent.
it's going to be like a bent type. Am I right?
Bent. Yep.
Yeah. If it is AB2, but two lone pair, so all the possibilities. What is this one now?
Is that one trigonal?
No, actually it's
No.
going to be tetrahedral, but due to the presence of two lone pair, it's going to again become bent. Look,
Tetrahedral bent. Yep.
Tetrahedral, but if you look the molecular geometry, then you can exclude the lone pair and you can say it is bent. If you are talking about the electron domain geometry, we say tetrahedral. It's clear?
Got it.
So that's I also I forget that it is not mentioning the zero lone pair, but then I checked the thing. Everything is not. They are asking all the possibilities. So when they will give you the exam and they give you AB2,
yep.
So make sure, ask your professor, do I have to assume it the zero lone pair, or I have to write all the possibilities with?
Oh, okay. Yep.
Okay.
Yep.
So that you are not going to make any mistake.
Got it. Understood.
Is clear?
Yes.
Okay. Now let's go to the next question. You
Okay,
did 12.11. What's
yep.
the next
question?
question?
Is 12.14. I wanted to just quickly mention that I got the syllabus from from the instructor for the for his organic class, and and it has on there the textbook and all that stuff. So I found a copy of the textbook on Amazon for like $15. So I ordered that, and
what book they are using? Like what writer?
Let me see. It says Seeger and Slabaugh and Thompson. Let's see, 8th edition. It's I'll type it in the message here.
You can email me. It's better. It stays there.
Yep.
Okay, Seeger and okay. I have to check. Maybe I have it. I'm going to double check this one.
It's I'll be able to send you the syllabus.
Okay, no problem.
All right.
And if you can get some past paper, ask him or practice. Okay.
All right. Yeah, I'm gonna definitely see if he can give me some practice exercises.
Okay, then let's go. Okay, now let's start with this 12.14. Am I right?
Yes.
Diethyl ether has a boiling point of 34.5 degrees Celsius, and 1-butanol has a boiling point of this. Both of these compounds have the same numbers and types of atom. Explain the difference. Okay, now just look the picture here. In this one, I will make this here so I can explain better. HC, because you haven't done the organic chemistry, so I'm going to explain what is. They already have written the name, so no problem here. The left hand side is what? Diethyl ether.
Yep.
Now I want you to give me the answer, because I gave you some hints in the previous question. So you can use that hints. Sorry, this is 2 carbon. Sorry, 2 carbon here. This is diethyl ether. Now think by yourself. This is diethyl ether. You can use the previous question which when I was explaining those things to you.
Yeah, so this one cannot hydrogen bond anywhere. It has
yes, because we have oxygen, we have hydrogen, but the main problem is oxygen is not attached with hydrogen. Carbons are attached with hydrogen. So hydrogen bonding is not possible in this case. But in case of 1-butanol, where the hydrogen bonding is possible?
On that hydroxide or hydroxyl group, right? On the end? On the OH?
Yes, because in this case you have 1 oxygen directly attached with hydrogen, like this one. So it's going to make a bond polarize. And now I'm not making the whole other thing, but the other molecule, other like a 1-butanol. So in that case, what happens? The oxygen of that molecule, this is another one, attached with carbon and so on, is going to make a hydrogen bond with each other. The oxygen, the negative part of the OH bond of one molecule of butanol will interact with the hydrogen of another molecule, hydrogen which is directly attached with the oxygen, that hydrogen, not with the other hydrogen, because these hydrogen are not so polarized. These bonds are almost non-polar. We consider them non-polar because the difference is very low. Only this hydrogen is polarized and giving you positive charge. The same situation happens with other molecules, with the OH bond. And now what happens? The H of one molecule will interact with the O of the another molecule, and they make a hydrogen bonding. Is it clear? Similarly, another molecule like the another butanol molecule, maybe like here, like this one, OH, carbon. So this one is going to also interact with this one, make a hydrogen bonding. Is it clear?
Okay. And because it can it can hydrogen bond, that's why it has a higher
that's why the boiling point of diethyl ether is low as compared to the 1-butanol. So hydrogen bonding is only possible when hydrogen is directly attached with either oxygen or nitrogen or fluorine.
Okay. Okay.
When hydrogen is attached with carbon or something else, they can't make hydrogen bonding. Is it clear?
Yes. Yep.
Okay, now let's...
Yeah, that makes sense for sure. It's 12.15.
Okay, read the question.
It's asking which of these pairs of substances would you expect to have a higher boiling point? And the first pair is...
Before we do this question, let me briefly explain something. And then you will give you have to give the answer.
Yeah.
For intermolecular forces, of course, the ionic bond is the strongest force. We don't consider intermolecular as ionic force. Ionic bond is the strongest thing. But beside ionic bond, I'm going to the covalent bonding. The strongest is the hydrogen bonding. Hydrogen bonding is the strongest.
Yeah.
Oh, sorry, and not hydrogen bonding. I'm going to write. The next is ion dipole. Ion dipole interaction. Ion dipole interaction. Ion dipole means you have suppose positive ion and you have something covalent molecule like water. Water is a covalent molecule with negative and positive pole, polar molecule. So now the attraction between them is going to be higher after ion-ion interaction, because the highest interaction is between two ions, positive and negative. Then come ion dipole. Third number comes dipole-dipole interaction. Dipole-dipole interaction, like between the two polar molecules. One more polar molecule like water, for example. Another water molecule is like this one, and they interact with no, sorry, this is I'm making wrong example. Dipole is, let me I will show you. HCl, for example. HCl, negative, positive. And now another HCl is this one. And now that attraction between positive pole of one molecule and negative pole of other molecule is, that's called dipole-dipole interaction. But before this, it comes like the one ion is the highest priority, like a highest interaction, then come ion dipole. Third one, this one I can say it is 4. Third number is, which I miss here, is hydrogen bonding. Hydrogen bonding. Hydrogen bonding is between The hydrogen of one molecule and oxygen of other molecule attach directly with either nitrogen, fluorine or oxygen. Now in this case I can give you the example of water, because hydrogen is directly attached with oxygen and another water molecule. I am taking this one, so this is going to be another one. So hydrogen bonding is stronger than dipole-dipole interaction. So I am giving third number, this one. Dipole-dipole come after that. And now the next one is called London dispersion forces. Now remember, London dispersion forces are present in all of them, whether they are polar molecule, non-polar molecule, whatever, every molecule, everything has that London dispersion forces. And what are these forces? It's like you can say temporary dipole. For example, one molecule is neutral, even hydrogen molecule. Suppose this is H and H molecule. This is nucleus, which is positive.
Yep.
And suppose a time comes when electrons are in the molecule are on one side. This is H2 molecule. Let me I will make like during the movement of the electron, a time come when the nucleus are on the one side and electrons are on the other side. So this portion will be negative, this will be positive. And same thing is with another molecule. Both nucleus are on the same side and electrons are on the other side. So this positive and negative interaction, which is temporary, is called London dispersion forces. These are the weakest forces, you can say, but they are present in all of them. So let's start with this.
Is that
and strong?
Is that the kind of forces that's either ion induced or dipole induced?
Yes, you can say no. It's not ion induced. It is like a temporary dipole, you can say, but it can be due to ion induced. But normally it is not due to ion.
Okay.
But it is present in all of them. Okay.
Do they increase with molar mass in size? Does the dispersion forces increase with molar mass?
Dispersion forces.
Is that the same thing? Or no?
No, it's not depend on molar mass.
Okay.
It actually is just the movement, and it's very weak force. But definitely, more mass means it's going to like a more attraction or something like that one. But it's not going to, because it's going to make like difficult the boiling and things.
Okay. Okay.
Okay, but let's go to the which question you are asking. 12 point.
12 point. Let me see.
15.
I'm gonna drag it down.
12.15. Now you decide. First of all, remember, non-polar molecules have only and only London dispersion forces. Non-polar molecules. So first look which member of each pair of substance would you expect to have a higher boiling point. In other words, which one you expect lower boiling point. Okay, in this case we can use the mass for boiling point. Which one is heavier, oxygen or nitrogen?
Oxygen, right?
Oxygen is going to be heavier. So we are expecting higher boiling point for oxygen.
Right.
Because both of them are non-polar. So now we can look the answer for this one.
Okay.
In this case, because both of them are non-polar, so now we can decide on the basis of.
Alright, it says O2. It has more electrons than N2.
And also not only heavier, but also what happens, because the atomic number of oxygen is 8, am I right?
Yes.
8. And O2 means they have 16 electrons. So during the movement of electrons, and also the oxygen has 6 valence electron, am I right?
Right, yeah.
And nitrogen has 5. So during movement, maybe the electrons are more closer to this part, giving more negative charge. Another molecule has more positive charge. So you can say mass and also the atomic number giving more electrons will affect the boiling point.
Okay.
Is it clear?
Mm-hmm.
Now in this case, the situation may be different. Now What are these molecules are polar or non-polar?
Well, I just from memory, I think CO2 is linear, non-polar.
CO2
Right?
is non-polar. You are right.
Okay.
Yeah, of course, it has like a two polar bonds, like, but they cancel each other and molecule is overall non-polar. Non-polar always have less boiling point than polar one. SO2, what about the structure of SO2? What is it,
It's
linear or no?
it's it's, it's bent, right?
It's bent because S has how many valence electron?
6.
Six.
They're all in that
And,
group.
yes, and 2 times 6, 12.
Sorry.
We have 18. And now I'm putting like here, 2 bonds here, 2 bonds here. Two to four. Okay, let me see, like this one is looks like a neutral. What is the shape is going to be here? According to VSCPR.
It, it says by my table it gives SO2 as
Because only
or,
for
like SO2 is it AB2E or no?
no, there is we can put the lone pair also, both things we can do it, because there are different possibilities for making Lewis, but the structure will be is going to be same.
Okay.
Let me I'm writing like this first.
Oh, okay.
In this case, what is the, let's see what is the formal charge of sulfur here.
Okay.
Sulfur has 6 valence electron.
Yeah.
Minus number of bonds here is
4.
4. So 4. There is no lone pair. 0 is going to be what?
Plus 2.
2 plus. So plus 2. Oxygen is going to be negative. Is going to be 0, 0, because if you calculate that one, is going to be 6. And what next? 2 minus 4
Yep.
is to be 0, 0. So let me make another type things. I am making like this. SO no, in this case what will be the what you predict the structure?
It'll be
Because we don't care about it. The structure is going to be same, it doesn't matter.
It should be
The structure is going to be
no.
Only 2, no lone pair, and 2 means no, but the structure is not linear, that's I know. Something, because plus 2 is giving the plus 2. Let me write like this first. Making 2 bond with this one. 2 bond with this one. And making octet this one. Now we have oxygen with how much? And it is donating its electron pair to oxygen. So let's see what is this in this case. Sulfur has 6 electron in the valence shell, minus 2, and minus also this one minus 3, you can say minus 3 and minus 2. What you will get? Plus 1, am I right?
Plus 1, yeah.
And oxygen at the other oxygen, not this one, so this is 4. This oxygen is going to be 6 minus 1 minus 6 is going to be minus 1. So this looks better than that one. So in this case, if I predict the structure of this one, SO2, what you will get? Central atom is sulfur. Sulfur has 3 bonds, because this 2 electron is also single bond. So out of 3, 1 is pi bond. So we don't consider pi bond. So I am considering bond pair we have 2, lone pair we have 1, Total we have how many? 3.
3.
So it is AB2E type.
Mm-hmm.
So what structure you predict?
Like B.
It's a bent, am I right?
Yep.
It's going to bend. So it is polar because they are not linear. So it's polar molecule. So which one is going to have a higher boiling point?
SO2.
And why it's going to be? Because the shape of the SO2 is not a linear, whereas carbon dioxide is linear and the dipole moment cancel each other, opposite dipoles, and make the molecule non-polar. Whereas SO2 is a linear shape and it's a polar molecule. That's why it's higher boiling point. What about the HF and HI?
HF and HI, let's see.
Because they fluorine and iodine are same group member. Fluorine, chlorine, bromine, iodine, like this.
Oh, so earlier we said hydrogen bonding can occur with nitrogen, oxygen, and fluorine. So if HF is a hydrogen bond, right? So as opposed to HI, which is not. So would HF be the higher boiling point since it has
HF is going to be
bonded?
Because the difference in electronegativity is going to be greater. As we go down, the difference in electronegativity is going to decrease. So in this case, HF we expect to be like a more, you can say, but double check this one.
Okay.
Because there are sometimes other factors. I want to check this one.
Okay,
it looks like HF.
It says HF. It says although HI has more electrons and should therefore exert stronger dispersion forces, HF is capable of hydrogen bonding and HI is not.
Yes, that's right. So in this case, what happens? Even we have more electrons in the iodine, but because we know the hydrogen bonding is only present in HF. So that's why it is going to be stronger with this one. Attraction. And stronger attraction means higher boiling point. Is it clear?
Yes. Yes. Excuse me. Yep.
Okay,
Yes.
and now let's go to the, which question?
12.17. It says explain in terms of intermolecular forces why NH3 has a higher boiling point than CH4.
This you can easily explain. You tell me.
Okay. So CH4 methane is not possible or is not capable of hydrogen bonding.
Very good.
But NH3 is, and since hydrogen bonding is the
strong has a stronger intermolecular force.
Is it the strongest one?
Not the strongest one, but it's stronger than other force. So like,
okay,
because the ion dipole is more stronger. But in the polar, non-polar bond, polar bonds, you can say, if there is no ion, in that case it is stronger. So hydrogen bond increase the boiling point because due to hydrogen bonding is stronger than dipole. Because now you are looking like a, and in CH4 we even don't, what forces you have in the CH4? What intermolecular forces?
Let's see. Is it just dispersion forces?
It's just a dispersion force. Because the difference in electronegativity is very small, so almost non-polar. So this molecule is a non-polar molecule. And there is no dipole-dipole interaction, there is no hydrogen bonding, only the London dispersion forces are there, which are the weak intermolecular forces. And that's why its boiling point is less than ammonia. And ammonia has a hydrogen bonding. London dispersion force is of course there, even in ammonia, but the main force, intermolecular force in ammonia is hydrogen bonding, which makes the boiling point higher because it increases the attraction between the ammonia molecules, within the ammonia molecules. It's clear?
Okay.
What next?
Let's see. The second part of that one is comparing KCl explain why KCl has a higher melting point than I2.
Now you tell me.
Okay. Yeah, KCl.
What type of bonding is in KCl?
That's an ionic bond, right? So
Yes, it is between the ions, positive and negative ions.
Mm-hmm.
And the attraction between the positive and negative ion or oppositely charged ions is the strongest force.
It's like it reminded me of like NaCl. Like it takes high heat to melt NaCl, right?
Yes. And that's why if you see, all ionic compounds are like a solid.
Uh-huh.
You're not going to see at normal condition anyone as a gas.
Okay.
Or even liquid. Of course, you can melt it, but under normal condition, you are going to see all of them are solid, because there is three-dimensionally there is attraction between positive and negative ions. Positive ions like potassium attract chloride ions from all sides, left, right, top, bottom, front, behind, and that's why this attraction is very strong. And strong attraction held the ions in a solid state in a crystal lattice.
Mm-hmm.
And you need a large amount of energy to separate them. That's why melting boiling point is high for ionic compound.
Okay.
But what about I2?
I2 is a gas, right?
I2
And that's,
actually is not a gas, it's like a solid normally, like a volatile solid. But what
iodine, my bad.
But what type of small molecule is this one?
It's
polar, non-polar?
It should be non-polar, right?
Non-polar. And what type of intermolecular force is there?
Is it just dispersion force?
Just a London dispersion. There is no dipole-dipole, no hydrogen bonding, no ion-ion interaction, and London dispersion forces are weak forces. So that's why its boiling point is going to be much lower than KCl, because KCl is ionic. Ionic is very like a strong interaction.
Okay.
Even more stronger than hydrogen bonding.
Okay.
What about?
Let's see. Yeah, that's it for that one.
What next?
Next is 1225. It says a glass can be filled slightly above the rim with water. Explain why the water does not overflow.
25.
12.25.
Glass can be filled slightly above the rim with water. Explain why the water does not overflow.
Well, I think this has something to deal with
surface tension.
Yeah, properties of liquids. Surface tension.
Surface tension, capillary action. A glass can be filled slightly because due to like a attraction between the glass and the water. Okay.
The water, what is it? It's attracted to the glass?
To the glass. Like that's why if you see like in the burette, if you look the burette has like a lower meniscus. You always read the lower meniscus. Yep. It gives a curve like this. It do not gives like a curve like this. Right?
Right.
Why? Because it rises more on the glass. More interaction, this one. You can say it's like a capillary action.
Okay.
And so just look what reason they are giving you there.
Alright, it's saying the water does not overflow. The water does not overflow due to the strong adhesive forces between the water and the glass and the strong cohesive forces between water molecules, mainly hydrogen bonds. Okay.
So water, why? What is the reason they are saying? It's strong?
It says the water does not overflow due to the strong adhesive forces between the water and the glass.
Because they are adhering to each other.
And then the strong cohesive forces between water molecules.
Yeah, they are like holding them together like that one.
Yep.
Okay? Due to that reason.
Okay.
And due to these forces, we also have a capillary action and other things.
Okay. Yeah, he did mention that capillary action.
And surface, like always you have seen like a falling drop of liquid always is spherical. All the falling drops of liquid are spherical in shape. Why?
Spherical in shape?
Yeah, because there is strong cohesive force between the molecule and they make create a surface tension. And due to surface tension, liquid try to reduce the surface to volume ratio. Surface to volume ratio. And the surface to volume ratio is minimum in spherical phase. Spherical. If you make a solid structure, it has more surface. If you make a spherical, it can accommodate more volume and less surface. That's why.
Understood.
Due to surface tension. Okay, what next question?
Next is 12.31. It says, predict which of these liquids has the greatest surface tension.
12.31. Okay, let me see where is 31. Okay. Predict which of the following liquid has the greatest surface tension. Ethanol or diethyl ether. Now let me explain something and then you will give the answer.
Okay.
So for surface tension, like suppose that these are the container and you have liquid molecules here. At the top layer, only you have like a bottom molecules are attracting towards themselves. They are attracted by left side, they are attracted by the right side. Another molecules also attracted by the bottom side. Of course, some molecules are in the gaseous state, but they have very little attraction. So there is an unbalanced force on the top layer of the liquid molecule. And due to this attraction, the surface layer acts like a stretched string. It acts like a stretched string. Okay. And greater the attraction between the molecules, greater pulling force among the molecules will give you like a more surface tension, greater surface tension. So now greater attraction, greater intermolecular forces among the molecule will produce more surface tension because there is a more pull toward inside at the top layer. So now look these things and condition and give me the answer for 31.
Okay.
Which one has more intermolecular force?
Would the C2H5OH have more?
What type of force you have there?
Hydrogen bonding.
What about in dimethyl ether? There is no...
Just the dispersion forces.
Just dispersion forces, you can say.
Right.
Okay. Yeah.
So
in this case, we can say like due to hydrogen bonding, which one is going to have like a more surface tension?
C2H5OH.
You double check this answer.
Okay. This was what, 31? Okay. Alright, it's saying ethanol molecules can attract each other with strong hydrogen bonds. Dimethyl ether molecules cannot. Why?
Yes.
And it says the surface tension of ethanol is greater than that of dimethyl ether because of stronger intermolecular forces, the hydrogen bonds.
That's right.
Note that ethanol and dimethyl ether have identical molar masses and molecular formulas, so attractions resulting from dispersion forces will equal. So this, so C2H5OH is
like because
ethanol.
there is more attraction, it is pulling the surface layer, the molecule which are present at the top. So the molecule which are inside there, like if exerting more in force in the downward direction. Okay. Let me explain this another way. Suppose there is a door, okay, and some students wants, like the kids, they want to go outside of the class, but one guy wants to go outside, and there are many guys behind, very powerful, they are pulling him in behind. So it's easy for him to go out or difficult?
Difficult.
Okay, if the guy behind him are only one guy and not so powerful, he is pulling him but with little force. So it's easy for this guy, another guy.
It would be it'd be much easier than this one, right?
So that's the same thing.
Maybe,
yes, you're right.
But like you mentioned, he's only a little bit like.
Little bit attraction, like London
Right.
dispersion force, something like that.
Okay.
And they're like a strong hydrogen bonding, pulling him from behind, and making it difficult for him to go out.
Okay. Okay.
Is it clear?
Yes.
What next?
All right. Next, let's see. Just did 44. 12.44. Calculate the number of spheres in these unit cells. Simple cubic, body-centered cubic, and face-centered cubic cells. Assume that the spheres are of equal size and that they are only at the lattice points.
Okay, let me. I have to do this.
Okay.
I will do this in next session.
Okay.
When I have to look this and do these things.
No worries. No worries.
Diagram with the diagram, another thing. Okay.
No problem. Yeah, we
What
can.
next?
Would you want to do a session like either tomorrow or Sunday or something?
When you want.
Yeah.
And whenever you feel comfortable.
Yeah, I would be willing to do one tomorrow.
Okay, no problem.
I'll knock these out. Like, I'd be willing to do a session each day, only if you're available.
Okay, then I'm available. So
Okay.
it's just I'm noting this 12.44. Am I right?
Yes.
Because I will take out the diagram and then you will do those things. Calculate.
No problem. Next, after that was let's see. This one's kind of similar, so we might have to do this one.
Which one?
12.47. It says vanadium crystallizes in a body-centered cubic lattice.
Yeah, that's on the body, like the solid thing we are going to do next in the next session.
Okay. Yeah.
Okay,
So
I will
we'll
take
skip
the
over that
picture and
one.
other things, and then we will do those things.
Okay. Okay. So we'll go to 12.86.
12.86.
Yep. Yeah, I can load it right in real quick.
Okay, consider the phase diagram. Okay, I will also upload this page. I can upload here, no problem.
I got it right now.
Oh, you're already uploading that one. Okay, it's uploading.
Yep.
Okay.
So this, right?
Okay. Yes. Now let's see this
A
one.
phase diagram.
Phase diagram of water. Now this portion, like there in the phase diagram, you have many things like here. This one is called area, like area A, area B, area C. How many areas are here?
3.
3. And these represent like if one is phase of water. Like A is solid phase of water, like you can say ice.
Yep.
B is liquid water. Sorry, C is here is the C is what? Liquid water, and then gaseous water. Okay. Like these things. So solid, liquid, gas, like we have.
Okay.
Now, in this case, consider, and this one is called triple point. This
Triple
one.
point. Okay.
Yeah, where 3 curves, and these lines are called curves or lines.
Yep.
These represents like at the line, you have 2 faces are there. Liquid and, for example, on this line, you have solid and also you have liquid.
Solid.
and
Okay.
liquid. You have both of them.
Yep.
And at this line you have solid and gas. At this line you have gas and liquid. Is clear? Gas
Yes.
and liquid on the line. And triple point you have all 3 faces that coexist here. So now let's start with this.
All right, so start.
Predict what would happen. Consider the phase diagram of water shown here. Label the region. A is area,
Solid.
solid water.
Mhm.
B is
Gas.
what? Gas water. And C is
Liquids.
liquid water. Liquid
Yeah.
water. Okay. So now we have solid, liquid, gas, all of them.
Mhm.
And now let's go like here. In this case, this is called triple point. Of course, they are not giving any number, but this one is called triple point where all 3 faces can coexist. This is the line if you want. Starting at A, predict what would happen if we did the following. Starting at A, we raise the temperature. We raise the temperature at constant pressure. You are starting at A, point A. You raise the temperature, but not changing the pressure. So if you raise the temperature, you will come here at the boundary. Right now you have only solid thing. Right now what you have?
Solid.
Solid, no liquid, no gas. As you move and you reach to the line, if you move, because when you are increasing the temperature, you are moving to the right, right?
Yes, yes.
Without changing the pressure. You will reach to the line, and line means now at the line you have solid and gas, both things are there. Solid and gas. Now if you further increase that one, it will cross the line and it will enter into the gas.
Yeah.
And what happening? It is converting into
Gas.
Gas. If we are start from the point A, because they are saying starting at A. So if you keep moving, like, you are not going to move to the liquid state. You will go to the directly to the gaseous state. Okay. Now starting at C, we lower the temperature. Now keep moving here to the lower, means going left. What happens? You tell me now.
Starting at C, we lower the temperature at constant pressure. So it would essentially, it would go from liquid.
What is here right now?
Liquid, right?
Only liquid.
Liquid to
now when you reach here at the red line here, what will be there now?
Solid.
Solid. Solid and liquid, both of them. At the line you have two states, solid and liquid here, both.
Oh, okay.
In equilibrium. And now what happens when you further decrease? It will cross the line, enter into the region A, and change into what?
All the way completely solid.
Solid, completely solid. Okay, starting at B, we lower the pressure. Now you are not changing that. Okay, 1 minute. Predict what would happen if we did the following. Starting, raise the temperature. Starting at C, we lower the temperature, okay, constant. Now starting at B, we lower the pressure at con. Now you are not changing the temperature, lowering the pressure. So where you are going to move from B?
Down to
Down.
C.
You are going to move down. So you will reach the line. At the line, okay, right now what you have here?
Gas.
Only gas. When you will reach at the line, what you are going to have?
Liquid.
Liquid and gas,
it's like
both.
It's condensing.
Yes, it's both of them. When you cross that line and enter into this region, you have only and only liquid. Am I right?
Right, right.
Now look, answer. I want you to see the answer.
Oh, 8-6, okay. Okay, yeah, for A, it says raising the temperature. A implies starting with solid ice and warming until melting occurs. If the warming continued, the liquid water would eventually boil and change to steam.
Yeah, melting happens here, like when they are in equilibrium. If you keep continuing raising the temperature, it will completely change into gas. Am I right?
Right.
They are saying gas or liquid, what they are saying?
They're, the terms that they're using are from solid ice to liquid water would eventually boil and change to steam. So, and then further warming would increase the temperature of the steam. And then for B, it says at point C, water is in the gas.
What they repeat again, starting at A, what they are saying.
Oh, actually, well,
read again this one.
Or for the region labels, it says the region containing point A is the solid. So yeah, they're using solid, liquid, and gas. Okay. But then they were just getting kind of specific with the, like starting at A, they said that it was solid ice, and then it changed to warming until melting occurs. If the warming continued, the liquid water would eventually boil and change to steam. Further warming would increase the temperature of the steam. That's
okay. So in this mean what happens? They are not taking only this point. Whatever the pressure is there, they are taking like going all the way like this. Because if I take the point, this one, and I will not get the liquid here in this case. If I just start from the point, but if I take the whole region A, then of course we can go like from here, liquid and like crossing and up to gas like this one.
Oh, okay, okay.
So
let's see. For B it says, at point C, water is in the gas phase. Cooling without changing the pressure would eventually...
at starting at C, what they are saying? Water is in the?
Gas phase.
Gas phase, okay. Okay, so C is gas, am I right?
Yeah, yeah. They said...
C is gas, sorry. The C is gas.
They said
B
A
is
is the solid
liquid.
region. B is...
Okay. C is gas. C is what? Gas. So when we are moving from A to B, we are going from solid to liquid. What we are going? Solid to liquid. And C is gas. So when you are moving from, this is low temperature. Yes, gas is present in all of them. Liquid is going to be here. So C is gas. So when you are moving from here to there, you are moving from solid to liquid. When you are moving from here, gas to solid, am I right?
Yes.
Gas to solid.
Gas
and
to
when
solid.
you are coming down, it is from
liquid to gas.
Liquid to gas, like that. What happens here? Here they become indistinguishable. Like if you go higher level, it's like a undistinguishable. You can't distinguish between liquid and gas like that.
Okay.
And what about here at the point here, where all the lines meeting each other?
Is it?
This is called triple point, and all three states coexist here.
So is it distinguishable or no?
No, it's indistinguishable, you can say. But in case if they give you the temperature and pressure, then you can predict what temperature, what pressure will give you all three states together. But right now, because we don't know the temperature, pressure is not given there, so I can't say that. Okay?
Okay.
So this line is solid and liquid, this line is solid and that's right, because solid become liquid, and after crossing B you will get what? Gas.
Gas.
Yeah. At high temperature.
Yeah, he said to know this one for the final, because he's going to do something like this on the final.
Okay,
So
what next?
Next is 12.90.
12.90.
It says name the kinds of attractive forces that must be overcome to A. Boil liquid ammonia.
Okay, you tell me what forces are there in ammonia. Like you can say the major attractive force.
So there's dispersion forces and then hydrogen bonding.
Dispersion forces is of course always there, plus main forces are hydrogen bonding.
Okay.
But you double check, they are in both of them or just only the major forces in the answer. Of course both of them are present there.
It says boiling liquid ammonia requires breaking hydrogen bonds between molecules, and dispersion forces must also be overcome.
Yes, because always dispersion force is always present there, and every place.
Okay.
What about melt solid phosphorus?
I think it would just be dispersion forces.
Is going to be dispersion forces.
Solid phosphorus. Would it be like
just
non-polar?
check the answer what they are saying.
Okay. It says P4 is a non-polar molecule, so only the intermolecular forces are of the dispersion type.
Dispersion force.
Okay.
Okay, dissolve CSI.
CSI in liquid HF.
CSFI is what type of compound?
Cesium iodine is the ionic, right?
Ionic compound, which has CS positive, iodine negative ions.
So that means, let's
and
see.
HF, and what is about the HF is?
That's hydrogen bond, right?
No, hydrogen bond is between HF and HF, but here you are dissolving CSI in the iodine. Sorry, HF. Hydrogen bonding is present between HF and HF molecule. But in order to dissolve you need attraction between the positive pole of HF and negative ion. That's like, you can say it is an ion dipole interaction. What is interaction?
Ion dipole. Okay.
Ion dipole, because you have ion and also you have a dipole which is in HF here. So you can say like the negative iodide is going to be attracted by positive pole of the HF, and CS ion is going to be attracted by the fluoride ions. So this is ion dipole. So look what is the answer they are giving you here.
Okay, it's saying CSI is an ionic solid. To dissolve in any solvent, ion-ion interparticle forces must be overcome. Also, hydrogen bonds and dispersion forces must be overcome to break the attractions between some of the HF molecules.
Because there is an ion-ion interaction between cesium and iodide ion.
Okay.
So you have to break this one. And you can break this one by ion dipole interaction, like dissolving, attracting the negative part towards H, and also dispersion force, you have to overcome the dispersion force. So because you are dissolving this one which has an ion-ion interaction in a crystal radius, so you have to overcome this one, and you can overcome by using the ion dipole interaction. Is clear?
Okay.
But they are only asking about the overcome, so ion-ion interaction. What about the last one? Melt potassium metal.
Okay. Let me see. Melt potassium metal.
Key.
Is it it's dispersion forces at the minimum, but
yes, there is no other force.
So, is there anything else?
No, I don't think anything else. So just like the answer, dispersion force, overcome, you have to overcome.
It says metallic bonds must be
metallic bonds, sorry. In metal, sorry, this is a metal.
Metallic
it's not a non-metal. Potassium has, okay, I will explain the metallic bond. This metallic bond. Metallic bond is considered just like for example, potassium. Potassium lose the ions, there are so many potassium atoms.
Okay.
And they have how many valence electron?
One
valence electron. They all lose the electron, and those are electrons. It's act like a cement, which bonds all of them together. And these electrons are moving around all the potassium atom, just like it's cementing the whole thing. And this is called metallic bond. It's just like the metallic bond is just like it's positive ions, the number of positive ions are dipped in a sea of electrons, and these electrons are just like acting like a cement, which keep them together. Clear?
Okay.
They are not. These electrons are free. They can move around all of them. So this is the metallic bond.
Okay.
So they are giving the metallic bond only.
That's all it says. It just says metallic bonds must be broken.
Must be broken. Yes, you're right. In all of them, like sodium, potassium, you have to do like this metallic bond.
Okay.
Phosphorus was because it was a non-metal. This is not a non-metal. This is a metal.
Okay. Okay.
So that's why we need that one.
Okay.
What next?
Next is the last one of this chapter. It says 12.91. It says, which of these indicates very strong intermolecular forces in a liquid? And it's giving, there's four, it goes A through
very
D.
Strong intermolecular forces in liquids. Okay.
And it says to skip, the teacher said to skip C. I'm not sure why, but maybe we'll figure out.
They look very important. D, very low vapor pressure.
Which
of these indicates very strong intermolecular forces in liquid? A very low
surface tension.
Mm-hmm. Liquids are definitely not an ionic compound, because I told you under normal condition, liquids are generally molecular, covalent molecule. Of course, after melting we can get the liquid. So because they are generally asking about the liquids, I am taking like a hydrogen bonding is going to be much stronger. Just look the answer.
Yeah, it says.
Oh, sorry, sir. They are saying a very low surface tension.
Yeah, it
They are not
says.
saying it's strong.
It
Oh, sorry,
says.
sir. This is opposite. A very low surface tension.
Yeah, it says a low surface tension means the attraction between molecules making up the surface is weak. Water has a high surface tension. Water bugs could not walk on the surface of a liquid without a low surface tension. Let me see. Which of these indicates very strong intermolecular forces in a liquid? A very low surface tension. So that would mean.
Oh, we have to look like one of them, right? Which of these indicates a very strong intermolecular forces? So very low surface tension is not, because strong intermolecular forces means a strong like a more high surface tension. A very low critical temperature. A very low boiling point. Boiling point is also not possible. Like if there is a very strong intermolecular forces, the boiling point is going to be very high. So also this is not possible. A very low boiling point. Oh, and very low vapor pressure. And very low vapor pressure. That's also correct.
D, is
So,
it D?
D, it looks like a D. I have to check the critical temperature and what, but right now it looks like a very low vapor
Oh,
pressure.
I think maybe he meant skip part B, because we didn't go over critical temperature.
Yeah, that's why normally we don't do that. That's how even I have to check that one. But D is, what is the answer here?
It says, oh, okay, now I've scrolled down. It says thus.
Answer is D?
Yeah, it says D. The only choice D indicates strong intermolecular forces in a liquid. The other choices indicate weak intermolecular forces in a liquid. Okay. So it says low vapor pressure means it is difficult to remove molecules from the liquid phase because of high intermolecular attractions. Substances with low vapor pressures have high boiling points.
I gave you the one example. One guy want to exit the class, escape from class. Others are pulling him inside the room. The same thing is here. When there is a very strong attractive force between the molecule, they do not allow molecule to go into the vapor phase, exit the liquid surface, am I right? So that's the answer, D.
D. Yep. Yeah.
And what about if a liquid has very low vapor pressure? What do you think? It has a higher boiling point or lower boiling point?
I'm remembering from what the teacher explained, if it has a low vapor pressure, then it would be a high boiling point, higher boiling point.
Higher boiling point. Let me explain this thing. Boiling point definition is that because what happens, the water, whatever the liquid is there, water or any other liquid, they want to exert pressure to go into the vapors. That we call like vapor pressure also. Also another downward force is also vapor pressure. But they are also exerting pressure to escape from the liquid and go to the gaseous state. Now from the top, we have atmospheric pressure. And at the normal condition, the atmospheric pressure is 760 torr, or mm of mercury, 1 atmosphere. So suppose you have two liquids, A and B. A liquid and B liquid. A molecule has a vapor pressure of 300. B has a vapor pressure of 400. And of course the atmospheric pressure is same in both cases, 760, 760. So where it is easy, which liquid is easy to escape and go into the vapors? Because the atmospheric pressure is pushing the molecule again into the liquid body. Molecule want to go into the atmosphere. So one is vapor pressure, you can say, in the upward direction. So what is the difference between here and here? 760 minus 300.
460, yeah.
So what is the difference here in the liquid B?
It'd be 360.
So where you are more easy to escape?
And this one, yeah?
This one, because the difference is less. they can easily overcome by some other resources. By gaining a little energy, they can increase the vapor pressure easily and become equal to this one. But here they have to get more energy in order to balance them. Is it clear?
So
To
if
lower the vapor pressure, higher the boiling point.
if we climbed a mountain, would we have there'd be higher
It's more
vapor
difficult to
pressure,
hire
right?
Mount Everest because a big difference from your ground level and other level.
Mm-hmm. So
Okay.
so would they have a high vapor pressure?
They have higher vapor pressure, but it is just like, look here. This is a mountain, okay?
Mm-hmm.
Mountain. One person is here at this place. Another person is at this place. Which one is easy to reach to the top?
This one.
This one. Because the already higher pressure, the difference is less. It's clear?
Mm-hmm. Mm-hmm. Got it.
So, less vapor pressure, higher boiling point.
Got it. Got it.
Okay, what next question?
That was it for 12.
Okay, I will see some question from here, this one. Hold on just 1 minute. Maybe I have some question. This was intermolecular forces, am I right?
Yes. Yeah,
IG.
these two chapters I did not do when I was at the community college.
Mm-hmm.
They actually skipped these and they didn't even touch on them at all, and even in general chemistry too.
Mm-hmm. Okay, let's start this one. And you give the answer.
Okay. I'm just putting my stuff away. Okay. Alright, so for number 1, it's saying identify the characteristics of a liquid. Okay.
Mm.
Okay. So it would definitely be indefinite shape because it's variable, but the volume,
Yes,
but the
definite
volume,
volume. That's right.
the volume would be
Okay.
the same.
Mm-hmm.
Give the
What about second?
the change in condition to go from a liquid to a gas. Okay.
Mm.
The change in condition from liquid to a gas. Okay, would have to increase heat. Okay. I know it's at least increase heat, but let's see. So reduce pressure. But if I was going from a gas,
Mm. Okay, let's,
would it?
even if suppose we don't know the answer, at least you know the answer is going to be include increased heat, am I right?
Right.
So either the answer is going to be A or maybe C. So let's see this one. Now let's look the pressure effect. If you increase the pressure, you want to change liquid to gas. The liquid molecule want to go to the gas, but you are pushing them behind and again into the container.
Yeah, that wouldn't
So
work,
increase-
right?
It's not going to work. It's going to send them back again into the liquid.
The gas molecules would need more space to bounce around, right?
Yeah, it means like less external pressure to escape.
Okay. So
If
it'd
there
be,
many guards are looking at it, it's difficult to escape.
hmm
So it's going to be what?
increase heat or increase the pressure.
No, increase heat or
I'm sorry.
reduce pressure.
Reduce. Okay.
Because if you are increasing the pressure, you are sending them back into the liquid.
Okay.
So either increase heat or reduce pressure so they can escape. Okay, what about this
All right.
third?
What type of intermolecular force causes the dissolution of NaCl in water? Okay. Type of
Mhm.
force. All right. So I know it's a ionic compound. So
Mhm.
it's what causes the dissolution. Okay.
Like which is cause of dissolution, dissolving this one.
Would it be ion dipole force?
You're right, because it is the interaction between, you have to overcome the ion-ion interaction,
Mm-hmm.
but the forces which are going to dissolve it is the ion dipole. What forces you have to overcome is ion-ion, positive ion, negative ion. But what forces are going to be give you like dissolving this thing is the ion dipole, the attraction between the ion and the dipole.
And the dipole that exists
Dipole
with
is
the
like,
water,
for example,
right?
water. Water has a negative pole and positive pole.
Okay.
So the positive pole of water is going to surround the chlorine,
Mm-hmm.
negative ion. The negative pole of the water is going to attract the positive ion,
Okay.
and that's ion dipole interaction that is going to help in dissolving this thing.
Got it. Understood.
What about
That's
fourth
totally-
one? But if they ask which forces that you have to overcome, then it is overcome. You have to overcome the ion-ion interaction.
Understood.
But what forces causes, then you say ion dipole. So be careful about the wording of
Will
the
do.
question.
Thank you. All right. What is
Now
the
next.
strongest type of intermolecular force present in NH2CH3?
Okay, let me, I will make this NH2CH3 structure a little bit. CH3 is, I'm going to write like here. Let me, I will write this. CH, H, H, and NH2 is here. What is the strongest? They are only asking the strongest intermolecular force.
I know it's not ion dipole.
You are right, because
It's
I
not
don't
that
see
one.
any ion there.
I don't believe it's dipole to dipole.
Okay.
There's no hydrogen bonding occurring.
No, hydrogen bonding is possible, because if you take another molecule, you are just looking one molecule. If I take another molecule, NH2 here, sorry, this is NH here and lone pair here, sorry. So this is positive, sorry, this is negative and this is positive. So now there is a hydrogen bonding between them, because hydrogen is directly attached with the nitrogen. Clear? Sorry, this one is, I made a mistake here.
Right, like
It's
right
not
here, right?
clear. It is electron pair, sorry. Showing in this way. Okay.
So, since that's the case, would hydrogen bonding, that would be the strongest force present?
Yes, in this case, hydrogen bonding is very strong,
Now-
because hydrogen bond is possible.
Can it occur right here?
Which one? It will occur between the hydrogen of molecule, hydrogen attached with the nitrogen of one molecule, and the nitrogen attached with the other molecule like this. And also possible another one here. Like from all sides it is possible.
Mm-hmm. Okay.
What is about the next one? We did this one, fourth, fifth one.
All right. Which of the following statements is true? Intermolecular forces are generally stronger than bonding forces. Increasing the pressure on a solid usually causes it to become a liquid. Until a certain point, the potential energy of molecules...
Okay, one important thing, sometimes we don't know the correct answer.
Mm-hmm.
In that case, use the elimination technique, because some answers are definitely wrong. Everyone knows this is wrong. So
Okay.
you can also use that technique if suppose you are not able to get the answer directly.
All right.
Let's start with the first one. Tell me about. Is this statement is correct? A. I'm asking the A one. First, let's start with this.
No.
No, because intermolecular forces are the secondary forces.
Mm-hmm.
Bonding are the primary forces.
Okay.
Primary forces are more stronger than secondary. That's why we show just like a dotted line, something like
I was
that.
thinking of NaCl or
Yeah, NaCl is an ionic bond. Even if it is a HCl, it's a covalent bond.
Mm-hmm.
They are more stronger than intermolecular forces. Intermolecular forces are between two molecules.
Okay.
Okay. So it's like suppose your relation within your home is more stronger than with your neighbor.
Okay.
Okay.
Yep.
So now look at then. What about the second one?
Increasing the pressure on a solid usually causes it to become a liquid. Okay. If we increase the pressure, well, on a
Think
solid,
logically. In solid, molecules are very close to each other.
yeah, that
In
wouldn't.
liquid, they are a little bit far.
Oh,
In gas,
okay.
very
They're
far.
even farther. Okay.
Mm.
So that's false.
Far. Because when you are increasing the pressure, you are bringing them closer.
Yeah, we just make it more of a
So
solid,
making
right?
solid, not like a liquid.
Okay.
What about the sea?
Until a certain point, the potential energy of molecules decrease as they get closer to one another. Potential. Would that be true?
Yes, that's true. Why? Because what happens because they are saying potential energy of molecules decreases as they get closer to one another. When they are coming closer, for let's say HCl, negative and positive, let's assume this one. As the molecules comes closer to each other, there is like attraction between them. The positive pole is attracting the negative pole. But when they come very close to each other, their nucleus comes close to each other. And now there is a repulsion between the nucleus and also electron-electron repulsion become effective. So the electron-electron repulsion and nuclear repulsion, they become effective, more dominating when they come too close to each other.
Okay.
Okay?
Okay.
So that's why. So they can only, attraction increases, energy decreases until a certain like a limit. And the same thing happens when you are making a molecule. For example, if you are making a hydrogen molecule, two hydrogen atoms comes close to each other, energy is decreasing until they reach at a certain length. If you want to further make them closer to each other, now the nuclear repulsion is going to take effect and make it unstable. Is it clear?
Unstable. Okay.
Yes. The short range, those repulsions are the short range, electron and nuclear repulsion. So after a certain limit, you can bring them more closer to that one. That's why we call it bond length. Bond length is the distance between them when the energy is at minimum between them. If you want to bring more closer to the bond length, the energy is going to increase due to repulsion. Okay, what about this one, 6?
What is the strongest type of intermolecular force present in H2? Alright, so if that was this, strongest type, it'd be dispersion, right?
You're right, dispersion, because there is no dipole, no ion dipole, none. So dispersion is the strongest force in this case. What about
what is the
in
strongest
CHF3?
CHF3, okay.
Let me write the structural thing.
Okay.
Because C, and you can see like all these sides, H, and F. I am making only one molecule. You can make another molecule if you want.
Okay.
Let me make another molecule.
So 28 electrons is what I would have to work with.
You don't have to look 20 electrons.
Carbon can only
Is the
go
molecule is going to make a hydrogen bonding or not?
It's non-polar. So
no, it's not a non-polar.
It is.
Okay, look here. These guys
so
are balancing each other, hydrogen and hydrogen.
Hydrogen bonding can occur here.
No, hydrogen bonding cannot occur because I don't see any hydrogen directly attached with fluorine. Hydrogen is there, but they are not directly attached with fluorine. In order to get hydrogen bonding, you need hydrogen directly attached to either fluorine or nitrogen or oxygen. I don't see that hydrogen. And hydrogen-carbon bond is almost non-polar. This bond is polar because fluorine is very electronegative as compared to carbon. So this is highly polarized bond. So which atom is going to get the negative charge? Fluorine is going to pull the positive electron toward itself. and you will get two poles, positive and negative. Same thing is going to happen here also. No, yes. Because in this case, again, what happens? Of course, this bond is not polarized. This bond is going to be not polarized. But still, you can say even this is positive, this is positive. So there is going to be some attraction like this, because the molecule is polar. Okay, so what happens? What you think in this case?
So would it be dipole?
Yes, it's going to be dipole. Because both of them are polar, there is no hydrogen bonding, so definitely dipole.
Because it's strong. The negative force is.
And also with hydrogen and also carbon, they can attract each other, like this one.
Okay.
What about 8?
Identify the weakest type of intermolecular forces.
Identify the weakest.
Would it be A?
Definitely.
Okay.
Right. What about 9?
Choose the molecule or compound that exhibits dispersion forces at its strongest intermolecular force. Okay. So NaCl is ionic forces, right? Cl2 is, let's see, not Alright, just a second. HF, so this would be the hydrogen bonding. Okay. CO.
Which one is, yes.
Cl2, would it be? Because it's a molecule. The
CO2, I don't. Where is CO?
No,
CO or CO2?
Cl2, would the answer be B?
No, CO is going to be polar molecule. Oh, Cl2 you are saying. Cl2, right?
As the answer, yeah.
Yes, Cl2 is going to be answer because it's non-polar. Cl is non-polar, so definitely the strongest is going to be
that's the strongest it can do. Okay.
You're right. What type of force you think in the CO? The strongest
would
force
be,
in this CO.
if it's CO, let's see. Would it be dipole or?
You're right, because carbon is positive, like less electronegative than oxygen, so oxygen bears slightly negative and positive pole is carbon, so dipole. What about HF?
It's
what is the strongest force here?
The hydrogen bonding.
And what about in NaCl?
The ion, right?
Ion, right.
Okay.
You are right.
So
what about 10?
Some ionic forces, those are ion. Okay.
Yes. What about this?
Choose the molecule or compound that exhibits dipole forces as its strongest intermolecular force. Okay.
As its strongest intermolecular force. Definitely, dipole cannot be in the polar molecule. Cannot be a molecule which is hydrogen bonding.
Okay. So yeah, it can't be. It's definitely not D, and it's definitely not E. So let's see. So I'm going to focus on these three. What do I know about these? CNF. CF4. That looks like it would be a polar molecule.
No, it's going to be non-polar.
I'm sorry. Yeah, non-polar. It's like
because
it's like
they cancel each other.
CF4.
Like fluorine. Yeah. One fluorine is pulling here, another is pulling here. They cancel each other. Okay.
This one here is polar.
Now the thing is, we have to decide between this is polar, we already know, and because we already know, so we can pick this one. BCl3 is not a polar. Why? Let me explain this thing. Cl, and Cl. They are like a trigonal planar structure. Angle is 120, 120, 120. So they are balancing from each other. One is pulling here, another is pulling. It's like a balancing something like this. All of them. They cancel their polarity from each other. Because if three sides you will put like the same forces, one side on the, you put three more electronegative atom around the corner of trigonal planar, it will make the molecule non-polar. So this is non-polar because of the shape. This we already know it's an angular shape or bent shape. So this is going to be polar. And definitely when it is polar, this is going to have the strongest dipole. What type of strongest force is here?
Dispersion.
Dispersion. Same dispersion here. Dispersion here. And what type of force is here?
Hydrogen bond.
Hydrogen bonding. What about 11?
Choose a compound that exhibits hydrogen bonding as its strongest. Okay. I see hydrogen here, hydrogen bonding for A.
You're right.
C2H6. This one would be a non-polar molecule, I assume.
Yes. So what type of force exists here?
Dispersion.
Okay. What about here? SCl2 is, you can say it is similar. Okay. Sometimes it is very easy to predict the shape by comparing with something you already know.
Yeah.
For example, I know water. Water is what structure you know and bent, right?
Bent, yep.
Because I know the sulfur is belong to the same family, and chlorine also make like a single bond, like a hydrogen. So I know SCl2 is going to be similar structure as water, bent structure. So this is also going to be polar. This is non-polar. This, what about this one? You can consider this one also as a non-polar.
Non-polar, okay, because
Yeah,
the carbon
yes,
is bonded to 2 hydrogens and 2 fluorines, right?
right. So now the hydrogen bonding I only see here in this way,
Okay.
because oxygen is directly attached with the hydrogen.
This one was in one of those homework questions that we did together.
Yeah. So
Right?
that's the answer in this
Having
case.
like a
Clear?
higher boiling point. Yep.
Okay, what type of strongest force is there in C2H6?
Dispersion force.
What type of strongest force is here in SCl2?
Dipole.
Dipole. Okay, now let's do the 12th question.
Okay. Place the following compounds in order of increasing strength of intermolecular force. Okay. So this is identifying the intermolecular force and then.
It's better always first identify polar, non-polar, ionic something.
Okay.
So that makes your job easy.
So CO2 I remember is linear and it's
Non-polar,
non-polar,
right?
right? So that means
What about F2?
non-polar. So F2 would be non-polar, right?
Mm.
And then NH2 CH3. So and is this H3? Would there be hydrogen bonding there?
Yes, in this case you will get the hydrogen bonding. Okay, now you have to compete between these two. Both of them are non-polar. Which one you think, in order of increasing strength? Increasing strength means first you have to give the lowest strength molecular force. Which one is at the lowest intermolecular attraction between them? Between these two. We know these are going to be lowest, one of them. And this is first of all, this is going to be the strongest, am I right?
Mm-hmm.
So I need someone, first of all, even if I don't know these two,
Yep.
I can get the answer because I know this is the strongest, am I right?
Yeah. Okay.
So I
from
know this is the only here.
So
What is one?
what I was thinking was, I was first thinking, I was like, okay, I was thinking that this one was less, not as, I thought that CO2 was weaker than F2, but it turns
No,
out that it's not.
First of all, even if I don't know this one, why I got the answer this one?
Right, because it's the only selection there that we.
Because I need
Right.
this one here at the end, and I have this one only at one place.
Mhm.
So I already got the answer. But let me suppose if there is two choices, then what I will do? Carbon dioxide is non-polar, but it still has two polar bonds. They are cancelling each other, but still it has polar bond. But F2 has no polar bond. Both of them are same. So when the molecule which has same atoms, there is no difference, zero difference in electronegativity, that's going to be the lowest intermolecular forces.
Okay.
This one is non-polar because of the molecule shape, but actually they have two polar bond. One is pulling let me I will show you like this one. This one is pulling this direction, this one is pulling this direction. Maybe some another carbon dioxide molecule like here and here, maybe this is going to slightly attract this portion, right?
You're right. You're right.
So that possibility is there a little bit, but that's not possibility in the F2. Okay, so it's clear. So that's going to be the answer, correct answer.
Got it.
But sometimes even you without knowing though that you can get the answer here, like in this case. Because I know this is going to be on the right side. So I see just only why I'm going to pay attention on here. Only one has a like on the right side this thing.
Got it.
Is it clear?
Yes, I understand. Yep, that definitely made a lot of sense. Thanks for explaining.
So I will also ask you like to whatever your class teacher has given you the questions from your book. Read those things, the wording of how they explain the answer.
Yep.
Okay.
We'll
So you
do.
have to get them, and we will review the things after at the end, all of them together.
Yep.
So next time we are going to do like the chapter 13.
Okay. Do you want to? Should we start with the next session with those other two? Like I think it was like 12.44 or 4.1 with the unit cell.
Oh, you have to do that one. Yes, definitely.
Okay.
First, you are going to do that one. Okay.
Okay.
I'm going to double check those things because I have to see those definitely those questions.
Okay. Yeah, I'm gonna read over the chapter tonight and tomorrow morning. Just to review.
For that, because we need like the arrangement of the atom and molecule in different shape of the crystals. That's all we have to do. That's not too difficult. Okay, so we can do those things.
What time would work good for you tomorrow? You think?
What time is good for you? First, tell me about yours.
For me. I'm available at any time. I could do the morning, afternoon. I could do evening. Honestly, it's.
Okay. So tomorrow is Saturday, am I right?
Saturday. Yep.
What about 4 p.m. is good for you?
Yeah, 4 p.m. is good. Yep.
Okay, we'll do it 4 p.m. Okay.
Yep. Yeah, I'll make sure that I.
If you want early, we can also do early. It's no problem.
Okay. Yeah, I think 4 o'clock will be
Okay.
a good time.
In case if you want to change, just email me. Okay.
I will. Yeah. Same with you. Just email me or call me.
Okay.
Thank you, Jafri. I appreciate it very much.
Take care.
Have a good night.
You too.